Welcome back. In chapter 16, we look at the law of averages and construct a box model for illustrating some of these points. And in our review exercises, we'll have a chance to look at some different applications of using the box model to illustrate some of these rules of probability as they apply to sampling. In the first problem, we have a box that contains 10,000 tickets, 4,000 zeros, 6,000 ones, and 10,000 draws will be made at random with replacement from this box. Which describes the best describes the situation and why? Do we expect 1, 2, or 3? I'm going to let you vote. We can't do live polling in this using Blue Jeans. I normally would do it with I normally do a lot of live polls, so I really wish we could, but thank you for responding. Yep, just be brave. Just put out there your guess. It's fine. So some people think 2 or 3. So let's see. We know that the number of ones will not be 6,000 exactly. Okay. That's great. Everybody realizes that. Of course it won't be. The number of ones is very likely to equal 6,000, but there's also a small chance it will not be equal to 6,000. Well, it's not very likely to equal 6,000. You would have to get, that would be, remember, above 60%. So there's a very small chance of drawing every single one. It's not very likely. But number 3 is what we actually see is correct here. It's likely to be different from 6,000, but it's likely a small difference compared to 10,000, because as we saw earlier in the lecture, once you get out to 10,000 trials of something that comes out heads or tails, and ones and zeros are very similar to heads and tails. You could think about them in exactly the same way. Once you get out to 10,000 trials, there's a very small percentage of error. So it'll be different from 6,000, but only by a little bit. And we are on problems. So if your screen is frozen, can everyone else see our problems changing, or the exercises? Okay, great. Just checking. If we look at item 3, we have a gambler loses 10 times running, or 10 times in a row at roulette. He decides to continue playing because he's due for a win by the law of averages. A bystander advises him to quit on the grounds that his luck is cold. Who's right? Are they both wrong? What do you think? Should he take anyone's advice? Yeah, they're both wrong. The law of averages says that the chance of winning on the next roll of the next toss or throw of the ball is exactly the same as his chance of winning on any other play. There's no dependence among plays. It's not related to the law of averages. The chances stay the same every single time. The law of averages just says that as you accumulate more trials, you're just more likely to have less error. So in terms of, in an applied context of gambling, you're most likely, to be better off with a smaller number of plays, although it's still just chance. There's just greater variability. If a coin is tossed 100 times, it is not likely that the number of heads will be exactly 50, but it is likely that the percentage of heads will be exactly 50%. Thank you. This is false. If the number of heads is 50, the percentage of heads is 50. It's not likely that it will be exactly 50. Now here's a nuanced point that we will revisit again in this unit, which is really just 2 weeks for our short semester here. So that's why I like to preview ahead, especially for you, because it takes some time to sink in. So let's say you tossed a coin 100 times, 10 different times. So you have 10 different sets of 100 tosses. Then you'll see still that if you average across all of those tosses, you might see the percentage of heads will be exactly 50, might be 50%, but it could be 50% without any of your 10 trials of 100 tosses having exactly 50% heads. Does that make sense? Because we'd expect on each of those 10 trials of 100 tosses that there would be, the first one might be like in a heads to tails ratio, it could be 45, 55, you could have anything here. But you're more likely to have things that are close to the mean, but not exactly 50%. But remember, if you keep completing, this is, 100 tosses. And we're doing it over and over again. So I know you haven't got to this yet in chapter 16. We're building to this idea, but it's this idea that you can repeat the process over and over and over again, many, many times, and then get a distribution of your scores from each of your time repeating the process. That's a big idea that we're building towards. And the flip side of that idea being that when you do take your multiple sampling over and over, if you take an infinite number of samples, then your distribution of observed values is going to reflect the probabilities expected based on your outcome. And we will take that idea and break it down into how we can use that to help us decide when there really is a difference between two groups, statistically speaking. So that's how everything going forward is, going to unfold in a very quick and dirty way of thinking about it. Now in item 7, we have a quiz that has 25 multiple choice questions. Each question has 5 possible answers, one of which is correct. A correct answer is worth 4 points, but a point is taken off for each incorrect answer. The student answers all the questions by guessing at random. The score will be like the sum of blank draws from the box blank. Let's fill in the first blank with a number and the second with a box of tickets. Okay. So the score here will be like the sum of, oh, there we go, 25 draws, because there's 25 multiple choice questions. And the box looks like, to just expand this in a bigger area for us, like this. We have one ticket in the box worth 4 points, or that's it has a value of 4. And then we have 4 other tickets that are each worth -1. So this is our box. And you can see how the tickets in the box represent the possible outcomes. Our possible outcomes are to either get 4 points or to get -1, and there's 4 opportunities to get -1. Does that make sense? This is actually an important question to understand if you have any questions about it. The second idea, the second blank is asking you, yeah, it's not a number, it's asking you what the box of tickets looks like. Yep. Because this is technically, this box is our model. And we're going to talk about different models in terms of a variety of different research designs and statistics that we can apply to them. So we'll talk about models a lot. This is just giving us an early idea of how we can model probability for just a multiple choice test. But the box itself is the model, the possible outcomes. Okay. There we go. A box contains red and blue marbles. There are more red marbles than blue ones. Marbles are drawn one at a time from the box at random with replacement. If you win $1 if a red marble is drawn more often than a blue one. So you have your 2 choices, 100 draws or 200 draws. And we have to choose among these 4 options. Why don't you go ahead and vote? Which of the 4 options is the most correct? Is correct here? Which would you choose? Okay, so there's a variety of thoughts out there. In this case, it's actually the answer here is item 2, B. B gives us a better chance of winning, and let's unpack that a little bit. So you win $1 if a red marble is drawn more often than a blue one. So if red equals 50%, equals more than 50%. Okay. So with more draws, the percentage of reds is likely to be closer to the percentage in the box. And there are more red marbles than blue marbles in the box. So the more times you sample, the more likely you are to get a representation that reflects the actual distribution and representation of marbles in the box. That's why if we take 200 draws, we have a better chance of winning. And just to keep mapping this onto thinking about sampling, this might make some intuitive sense already to you too. Since we've already looked at the GSS population data set, if you sample a larger population, you're more likely to accurately represent the people if we just look at the representation of race, of participants by their race in a sample, we know that the larger a sample is, assuming random sampling, the better, as you get a larger sample size, the distribution of race in your sample is going to be a better and better approximation of the distribution of people by race in your population. That's why the GSS data set, or that's one reason why the GSS data set is very useful in health disparities research that often uses racial classifications. Because you want a representative sample. Oh, and that's it, because there was only 10 review exercises in this chapter, which, again, nice. There's fewer items here, so that's good. And it might be worth, I do recommend taking a look at the even numbered items in this chapter too, just to make sure that you have a good grasp of what's going on behind these ideas. And it looks like we have just a little bit of time left. Would you rather look at a couple of the even numbered items, or we can preview a little bit of the expected value and standard error stuff? We don't really have time to do much of it. Okay, well, let's do some even numbered items. And I have this open in the background here for us. I didn't just pick that kitten picture randomly. Isn't it cute how she's reaching for the sky? Like you all, she's discouraged by the kitten biting her butt, or maybe an exam score, but she's still climbing and climbing. So let you be inspired as well. I mean, heck, a week ago that kitten could barely walk. So if that's not inspiring. So yes, I like these gambling problems too. I think it gives us a nice way to unpack these issues in sampling. And even if you don't gamble or play, I don't really gamble at like a casino, but I sometimes like to teach my family members about gambling, for fun. We practice doing, the probability of gambling outcomes and things. And so that's a fun way, if you want to practice some of these ideas, it really can help with understanding it. Sit your family down with a bunch of dice and see how you go. Let's look at Let's look at 4 here. This is a good one. Item 2 is just like item 1. And incidentally, I actually have won some money at roulette. I have a friend who likes to go with her husband, likes to go to the casino in Detroit, and sometimes, you know, we go along, and the statistician in me just can't stand it. I have to do some roulette because of the fun odds, and it's actually works out kind of well. I mean, at MGM they make you bet $20, so you can distribute it, so you actually have a better than 50% chance of winning on each toss. But let's talk about some standard gambling setup here with a die rolled some number of times, and you win $1 if it shows an ace more than 20% of the time. So which is better, 60 rolls or 600 rolls? Well, first, the key with playing blackjack is that you have to get down card counting. This is what I was teaching my siblings at our last family gathering, was how to count cards in blackjack. It's tricky though. It takes practice. So note that 1, an ace, is 1 outcome out of 6. So there's a 1/6 chance, or a 0.16 or 16% chance of getting an ace on any individual roll. Actually, playing gambling games is, if you look at like professional associations of statistics, groups or statistics professionals doing gambling related activities at like meetings and stuff, it's a common trend. Actually, statisticians love maybe not actual gambling, but gambling in theory. So that's the best way to gamble, right? No losses. When I taught my family, we just played for Skittles, so nothing too big. So here we can keep in mind that we have a 16% chance of getting an ace on any individual roll. So now we want to know if it shows an ace more than 20% of the time. So that's more variable than it's still fun, even if you're not winning, it's still fun. I mean, I was still winning Skittles. I always win because I'm the house when I'm teaching my family, and the house always wins in casinos. So works out for me. And it could work out for you if you teach your family, because you get to be the house too. Anyway, see, gambling is so much fun to discuss. We can't even stay on this problems. The point here with part A is that we have more than 20% of the time. 20% is a score that's above our expected percent, so it's more extreme. So we would want to just do 60 rolls. If we did 600 rolls, we would be getting closer to the percentage of aces would be getting closer to 16%, so we'd have a low chance of getting that. So 60 rolls is a key idea here, because remember, as we increase our number of trials, we get closer and closer to a distribution that represents the expected probabilities. So now we have the same scenario. You win the $1 if the percentage of aces is more than 15%. Now, do we want to do 60 rolls or 600 rolls? Well, now since we just want the percentage of aces to be more than 15%, and we know that at 600 rolls, we would expect it to be getting it would be about 16%, or 16.6, 17%, but either way, it's above 15%. So this time we want to go with 600 rolls. Does that make sense? Because the variability plays in your favor. Now you win the dollar if the percentage of aces is between 15 and 20%. How are we most likely to achieve that end? Well, about 17%, because again, this is a slight underrepresentation. It would be technically about 17% or 16 and 2/3. Oh, okay. So the exact percentage is 16 and 2/3. So if we want to get the percentage of aces between 15%, which is below our expected value, and 20%, which is a bit above, we want to be, again, at a higher number of trials here, 600. And again, how are we most likely to get a percentage of aces that's exactly equal to the expected probability? 600, right? The higher the number of trials, the more likely we are to get, oh, well, I guess we would say technically, if we want to get exactly 16%, it would be 60 rolls, but I'm jumping ahead conceptually a little bit in my mind because we were just discussing the sampling distributions, and we'll be there before the end of the week. So let's not, I'll wait a little bit, but the idea generally would be that if you took a lot of trials, then your average number of aces would be more likely to be equal to, across all those trials, it would be more likely to be equal to exactly 16.23%, but that's different than just looking at this set of 60 rolls or 600 rolls. So this goes back, Stephanie, to that conversation between at the beginning of the chapter. So it's not that the more you roll, the closer you get to the average. It's that the more trials you take, the more the smaller the variability from the average. So if let's think about it like this. So today, in our simple examples, we talked a lot about what's called a binomial distribution, the 1-2 outcome, heads, tails. But the reason that we also look at the box model and the sum of draws is that when you start summing the draws of tickets from a box model, you'll see that if we did this a bunch of times, assuming that we have a 6-item box model like the one presented that we discussed earlier on, the 6 tickets, let's say you took one set of 10 trials and summed those draws. You take a second set of 10 trials and sum those draws. Well, here. So it goes back to this. So say you do 10 draws one time, and your draws are like, I wish we could roll die for these, but let's say your draws went 1, 4, 5. So those could be our 10 draws. I tried to put them down randomly. And I'm kind of building on what is in the chapter here to expand the idea, because we'll be at this idea basically by the end of this week. So it's good to start kind of thinking about it now. And then we took 10 draws again. If we take 10 draws another time, our draws are going to come out differently. So if we sum these, I don't know what they sum to, but if somebody out there wants to sum them, that would be awesome. If we take 10 more draws, we'll see they'll come out in a different random assortment of numbers. I'll randomly select some more numbers now. It's not random because I can see the other numbers there, but I'm trying to be random here. It's really not possible to try to be random, but anyway, it's going to come out a little bit differently. Thank you. And if we sum this one, again, it's going to sum to 29. So we could keep taking 10 draws from the box and keep summing the numbers, but if we did that over and over and over again, 10,000 times, we took 10 draws 10,000 times and summed the sum of the tickets from the draws, we'd see that the total range of sum of draws would be from 10, right, if you got 1 each time across your 10 draws, to 60 if you got 6 on all of your 10 draws. And either thing could happen, but the probability of getting 10 is low because there's only, there's all these other numbers in there. You'd have to get 1 on every single, on each draw. So we'd have, we'd have just a small number of trials that would have, remember this is for 10,000 times our 10 draws. We did 10,000 trials of 10 draws, right? And we start plotting the sum. We start making a histogram out of the sum of the draws. We'll discuss this more on Thursday, but it'll be good to get an idea of where you're going. You plot the sum of your draws on this distribution. Down here, the sums are 10. Up here, they're 60. And you'll see if we start doing that as we get, just like these ones centered around about 30, the 30 will be our mean, is the most likely mean. But if we could plot each of these, and I can't plot all 10,000, but we'll see that 30 is most likely to be our most frequent score. And eventually to plot this out here with a smoothed curve, you'd see it end up like a normal distribution where the more extreme sums are less frequent. You can see they're less frequent on the extremes, but the sums that are in the middle range are more frequent. They're more likely to show up just based on the simple probability of how the sums add. And this is the basic idea behind sampling the normal approximation for a probability distribution. That if you take a very high number of samples or an infinite number of samples, then your number of draws approximates the population distribution, which is layering in kind of another idea. Does this make a little bit of sense here? This idea that we can plot the sum of draws for each of our 10,000 draws. That's good. So this is a big idea we're unpacking, and you'll see that the sum of draws is just giving us a nice way to first think about variability, because in our next unit, or in our next chapter, excuse me, we're going to talk about, really dig into the expected value and the standard error. And the standard error is a really important idea that I think we're well prepared for, because we've already discussed the RMS error and error in some other contexts as well. And I know we're right at the end here, but I thought there was one more item. It would be nice to take a look at number 6. And maybe number 8, since everybody loves gambling so much. According to genetic theory, there's very close to an even chance that both children in a two-child family will be of the same sex. There are 2 possibilities. 15 couples have 2 children each. In 10 or more of these families, it will turn out that both children are of the same sex. Or 30 couples have 2 children each. In 20 or more of these families, it will turn out that both of the children are of the same sex. And which one is more likely? So the this is, oops. Okay, I couldn't see it. So if we look at the individual probability of each of these, so if we have 10 out of 15, that's the same, the same as 20 out of 30. They're both equal to 2/3. But it's asking us which possibility is more likely. It's saying that in 10 or more, it will turn out that both children are of the same sex. So we know that we're looking for something that exceeds the even chances. So if we want to get above, 2/3 that have children of the same sex, that's a more rare score. So we want to have the option 1 with the smaller number of trials, because it's going to is more likely to have some extreme variability in there. And are you still with me out there? Okay, let's do this last roulette problem. Okay. A gambler will play roulette 50 times, betting $1 on 4 joining numbers each time, like 23, 24, 26, 27. They're next to each other. If one of these 4 numbers comes up, she gets the $1 back, together with the winnings of $8. If any other number comes up, she loses the $1. So this bet pays 8-1. And there are 4 chances in 38 of winning. So let's try to fill in the blanks. her net gain in 50 plays is like the sum of 50 draws from a box, right? Because this is our number of trials. She plays 50 times. And what does the box look like? And this is a box with 4 tickets marked $8. So 8 is here times 4 times. And then we have 34 tickets that are negative $1. Now we could write that all out, but it would just take a lot of time. It's really important to be able to accurately conceptualize the box. The box is the possible outcomes. It's not her bets. Her bets are not the outcome. These are just numbers she's taking a chance on, but they're unrelated to her winnings. She can either, there are 2 possible outcomes, winning, there's $8 and there's negative $1. And the outcomes have different individual probabilities, but there's a total then of 38 possible outcomes. So the box is like our population. And let's see. I know this is a tricky idea, but this is really important take-home point here, that the boxes are always made up of the possible outcomes. Yeah, and I think that looks like we've already discussed the remaining even items, but if you want to, let's see, there's only a couple left. 2 is just like 1, but if you want to just go for broke, we can do item 10. It's okay. Don't worry about it, Stephanie. I'm sure you weren't the only problem or the only person who was thinking that. This is a nuanced issue, so that's fine. Everybody's probably half asleep since nobody's really voting for more problems. That's okay. We've all done a lot of problems tonight, and you did a great job. I know we're unpacking a whole new tricky idea here, so just try to let it unfold, get some sleep. Research shows, my personal research and actual tons of research you can look into, students don't get enough sleep. So try to get some sleep tonight, and that sleep will help you to consolidate your memories about this topic. And we'll do number 10 if it looks like Joe is interested in doing it. So we'll just do it. What the heck? We're already right here. What the heck? Oh, there we go. case you're wondering, like, why is she doing all those extra things? It's because I should have I'm trying to keep our citation on each of our slides for copyright reasons. That's all. It's just what the heck? So please bear with me. I'm just trying to not break the law. Here we go. There we have it. Item 10, like magic. Like slow magic. "200 draws will be made at random with replacement from the box laid out below. If the, sorry, I just can't, it doesn't show, it always does that when I try to make the pen show up the first time. I always switch the slides. It's a real pain. If the sum of the 200 numbers drawn is 30, what is their average?" Well, if the sum is 30, we know that average is equal to the sum divided by the number of scores. In this case, there's the sum of the 200 items drawn, or excuse me, there's 200 numbers drawn, 200 trials that sum to 30. We have to think about this as our sum out of our total number of trials, or the n. And I'm just inserting that we haven't yet formally introduced this in the book. I'm just previewing that n is a key letter you're going to see in a lot of upcoming things that always represents the number of trials or the number of participants. So what's their average? 30 divided by 200 is 15, or 0.15, or 15%. For B, let's look at this. If the sum of the 200 numbers drawn is -20, what's their average? Well, for B, if the sum is -20, we can just find the average the same way. We just take -20 out of our 200 draws. And this time the average is -0.1. Oh, this is the average, not a percent. I forgot. In general, how can you figure the average of the 200 draws if you're told their sum? We actually already did this. We know that the average is equal to the sum out of n. In this case, it's the sum out of 200. And for D, we have one final option here. There are two alternatives. Winning $1 if the sum of the 200 numbers drawn is between -5 and +5, or winning $1 if the average of the 200 numbers drawn is between -0.025 and +0.025. Ooh, this is tricky. Which is better? Or are they the same? Well, what we need to look at in order to make a decision here is we really need to break down and put these options on the same units or in the same scale. So if the sum is between -5 and +5, what's the average? Let's just figure. Sorry, I keep thinking I'm going to sneeze. 5 out of 200 is equal to 0.025. So these numbers didn't come from nowhere. You can see that. And we know this would be a positive 0.25 here, or if we did a -5 out of 200, we would end up with a negative 0.025. So they're this exact same range, and in this case, these two alternatives are equivalent. Can you all see that? They're just the same idea there. So that's great. We've done nice coverage here of the law of averages, and good luck with the next unit on the expected value and standard error. Keep on climbing.